Good morning, everybody, and thanks. Do you hear me well? I think yes, right? So, thanks, Gediminas, and also you for the organization of this very nice conference. So, what I will try to tell you today is how mixture, that are the theme of the workshop, can really allow us to do a lot of things when we combine them with Raman coupling. This is not a scoop. But it's very nice is that we can understand them in a similar way when we are in the bulk and also when we are in the lattice. So this thing is for changing. Okay, so the fact that Raman coupling is a magic tool, I think is not in this audience. One shouldn't insist too much. And this is true both in the bulk and in the lattice. And just a very biased example of recent work. Indeed, one can have a super solid, as also already demonstrated many years ago by Ian, but also topological gauge theory. And on the lattice, one can have, using synthetic dimension, can have quantum Hall physics, but also now we start getting strong interacting system. This is fermion influence. So, okay, but a nice thing that at least in the bulk, this is obvious to everybody, we can understand very well the situation in which the Raman coupling is strong or when it's strong or when it's weak. Because in both cases, we can understand very well the system in low energy. So if you look to the weak situation, we have the three dispersion, in this case, three dispersion relation of the spin state that are well identified. So we have, since momentum is almost conserved, we have a huge gap. When the Rabi coupling is large, we have still a huge gap that is directly given by the coupling that separate two bands that are highly hybridized. But in both cases, so we can describe the system in terms of dress particles that live on the minimum of the dispersion. So in this case, we will have as many minima as the original number of particles, and here we have just one dress particle. And the nice thing is that with interaction, they give rise to very different physics. So it's like having a modified particle. And an example on this apply is precisely the supersolids triphase. So I won't say too much because Sarah will present it. But what I wanted to stress is that if we use this idea of describing the system as a mixture of these dress particles, and we call it this model, mixture model, we can not only very semi-analytically explain the phase diagram, but also explain the excitation mode of the stripe. These are the calculations without any fitting parameter. These are the experiments. And it's remarkable that very simple modeling of the system is working so well. But this is not only true when the Raman coupling is small, but also when the Raman coupling is large. Now we are in the situation in which we have just one, the lowest band has just one minima. But if we sit at the point in which we have, in this case, we have again just two components, we sit at the point in which the polarization is just zero, so it's half-half superposition. There we can notice that the effect, if we start with particles that interact very differently, we get an interaction that is changing almost linearly, and this, if we do math correctly, implies that the model, also at the quantum level, is described by having normal contact interaction plus a linear term. And this linear term at the end is nothing more than if we complete the square for lambda small, having like a sort of synthetic gauge field, but density dependent. So the nice thing is that this is precisely what one needs to achieve what is called the chiral BF theory, that is a theory that describes the edge of a fractional quantum Hall system in the continuum limit. In a sense, it was proposed actually by Ravello as a model to get 1D anion from 2D. Then there was some discussion, some quarrel where these were anion or not, and Kundu solved the problem so that saying that indeed this can be interpreted as anion. So where are the anion here? So to see the anion, what you have to do, we are in 1D, so you know that we can always remove the gauge field by a gauge transformation, or if you like, a Jordan-Wigner transformation. But now, in this case, precisely because this is descent dependence, the field that it changed this commutation relation. So they commute on site, but they see each other, and when we change, acquire a phase that is precisely controlled by this lambda. So this field contains really 1D anion, but as Jacques and collaborator showed, the main signature of it, okay, we will see before the main signature. Let me give you another way to interpret this, this phenomena that is, okay, and this was actually proposed by Gediminas and collaborator many years ago. We can still understand everything also in terms of having a density, a many-body detuning, sorry. So what does it mean? We know that having a gauge field means is equivalent to having a detuning, because imply a displacement of the minima. In this case, if we have interactions that are very different, there is a mismatch when we increase the number of particles in energy, so we have a many-body detuning, and then we can just replace it here. The nice thing is all this is working also at the quantum level, but this is essentially the idea. Okay, so as I was anticipating before, there are two very nice signatures that I want to remind, because we will see afterwards why. So there are the existence of chiral soliton. That is something quite obvious. If our interaction depends on direction, there will be, if we move in this case in the experiment to the left, the particles have notice attractive interaction, so they are bound, they are a soliton. But if they are reflected by a barrier, they change direction, they move to the right. Right, in this case, the effective interaction is positive, so it's repulsive, they're not bound, they dissolve. And the other signature is the asymmetric expansion of the gas, because the fact that we have a gauge field proportional to density means that the electric field is the derivative of the density. So if we make the gas expanding very fast, as here in the experiment, we see that the cloud take this asymmetric shape. Okay, just to say that this is not only true when we walk on the line, we have also completed recently a proposal where if we would replace the Raman with light with orbital angular momentum, so the kick now is not a momentum kick, but is an angular momentum kick, we can have similar physics, but now on a ring. And in this case, we have the winding number that is log to the density of the particle, and also we can observe that this, like on the line, we have that the speed of propagation of excitation by Bogolyubov is asymmetric, as one would expect. But okay, let me move to the anion part. So just to have a summary, we said we have the chiral BF theory, and we know how to realize chiral BF theory in the lab, as was done quite some years ago now. And also, we know that if we put this model on the lattice, one gets what is called 1D anion. So we have the usual recipe, as you may expect. The gauge field here, by pair substitution, become the phase of the tunneling. So what we are asking, having a phase that is depend linearly in density. If we have that, again, we can think of reabsorbing it and write as free particle, but these free particles are anions. And recently there's been, this was for many years something just theoretical game, but since the last 2 years there's been an experiment. So where been probed both ground state properties and dynamical properties. So Hans Christoph, they show that as one would expect, there is an asymmetric momentum distribution of particle, and dynamically, as was shown in Harvard, if one put two particles, they would expand asymmetrically. So this would be the analogous of the asymmetric expansion that we observe in the experiment. But now the question is, okay, we can follow this path, we can follow this path. So what happens if we put a lattice on this model? And as you may guess, what you get is precisely a new version of an onion-Hubbard model that we call Raman onion-Hubbard model, and I will show you why, where this theta angle now can be directly related, as you may expect, to the imbalance interaction in the synthetic ladder. So how we get to there? All this can be understood as in the bulk, using dress particle picture. So which is the idea? The idea is that now we add the lattice, we get a synthetic ladder, and if we look to the low energy excitation of the synthetic ladder, we can map to an effective model. In fact, the effective model that is coming out is a triangular ladder, and can be also exploited for studying quantum magnetism, as we did in this work, also that include Luke and Maciek. And I have no time to explain you, but for one nice thing is that not only this is a way for getting a frustrated magnetism without geometric frustration, but also give another way of understanding the phase in this model. For instance, we show that this curious phase that is a chiral superfluid, where current is going or left or right, actually correspond to something that is very easy to understand in the ladder, that is just bias ladder phase, where occupation is greater spontaneously, it's polarizing on one leg on the other, that is nothing more than a plane wave phase from the point of view of the bulk. Okay? But since I have no time to discuss that, I will just go directly to the model for anions. So here, as in the continuum, what we need strong imbalance interaction, and the final result is a model that encompasses what you would get in the continuum, and these are the hero of the story. So, just to show as very simple, we have now the Raman beams that produce the spin-orbit coupling, and we have also the lattice, depending on the projection of the wavelength of the two beam. We have a synthetic flux that we can tune, and also we have interaction that we assume to be tunable, like in potassium. And for the moment, let's look just at a single particle level. Same argument as before, very easy, 2x2 matrix, I can calculate the band. And now I take, as in the topological gauge theory experiment, I take the Raman coupling sufficiently large so that the two bands are well separated, and the moderate flux such that the dispersion is just one minima. So I can describe this system as an effective chain in which the tunneling is renormalized, but most importantly, the composition of particle change. And so the model that describes the system is just 1D Bose-Hubbard model. But now, what happened? If we have not just symmetric interaction, but we have different interaction between up and down, what we get, again, we get an effect of many-body detuning that displays the band. So what is natural to expect, and indeed, if one is doing calculation carefully, what is getting is precisely a term that is a current density term, but now on the lattice. And again, mutatis mutandis, what one is getting is that this theta angle is controlled by the combination of the flux times the imbalance of the interaction. And so we can essentially show that there is this, we are really parallel to the situation in the continuum where we replace the current in the continuum with the current on the lattice. Okay, if one is more careful and include all second order correction from the upper band and also the fact that there is still a tiny second order coupling, one get a model that is effective model that is quite accurate, that describe in a sense that if we use this effective model and we compare with the original ladder, we get essentially the same physics, and this is a new version of anion-Hubbard model, because as in the continuum, if theta is small, we can complete this term to the exponential. But if theta large, and also we consider T2, we still get sort of anion, but with slightly different properties. And a big advantage of doing this in this system is that we are not limited by finite few number of particles, but we can consider, while keeping the lowest band approximation, an arbitrary number of particles and density. Okay, so let's check that everything is in order. Indeed, if one would compare the two models, we see that there is the asymmetric density distribution in momentum, and this density is moving depending on more particle we put, larger is the fat, as we expect, and here is the fit. And also, let's see what, to compare with the continuum, let's see what, if there is some correspondence with the observable. So what we expect is to see something analogous to chiral soliton, and this indeed is the case, because if one is solving the system for two particles, so this is the solution for two particles, these color states are essentially the bound states that are out of the continuum. So these bound states are the two particle parallel of what are the chiral soliton in the many particle regime. And then also we would like to see something that is connecting to the fact that now we have a self-generated magnetic field. And so we should see some sort of asymmetric expansion, but this is actually what was seen by the random walk of two particles in the experiment of Marcus Greiner. And we indeed verify that the effective description of the ladder is extremely good. And also we compare with our Raman anion-Hubbard model with the original anion-Hubbard model, and we see that indeed, as we expect, when theta is small, we get the same behavior, and if we move away, we have a different behavior, but with similar phenomenology. So just to summarize, because I'm getting close to the end, now we have more possible platform to explore the anion-Hubbard model. So there is the Floquet root, that is the one demonstrated in Harvard, and now they have also shown result for a few more particles, but it's essentially limited to few particles. Then there is the impurity root, that is the one in the experiment of Hans Christoph. And then the Raman root, that still has not been realized in experiment, but Sarah and the people in the lab are working to make it possible in the future. So what is the difference in this model? So they coincide with the original anion-Hubbard formulation for small anionic phases and deviate for larger. We have also this additional tunable next to leading order tunneling. But we have the advantage is that we have many body regime accessible and in principle long lifetime, because we are not using Floquet and photoscattering is not so serious in here for the power we need. So what is the next goal is really to see which are the many body phases that exist in in this model. This has been studied up to now theoretically, and here what we would like to do is not only to encompass the onion-Hubbard model, but really going beyond this regime. For instance, Luis Santos and collaborator demonstrated that the onion-Hubbard model can contain partially paired phase that appear when the anionic phase is large. That means that the system is close to be described by a pseudo-fermion. What is a partially paired phase? It's just a phase in which we have a condensate of single particle that compete with condensate of this two-particle bound state I show you. And the nice thing is that we see that this two-particle calculation show that we can have that the energy of the two-particle state can be comparable to the minimum of the band, and this we can achieve for not too large theta, but taking into account also this second neighbor tunneling that the model has. So we have the hope that like this we can assess different phases. And also another thing would be, okay, once we have one chain, why we don't try to get more and to couple them? And actually we can think of doing it in the system. So suppose that we have two synthetic ladder that reduce to this Raman wire. And now what we would like to do, we would like to couple them, and if we have opposite phases, the net effect would be having a density-dependent flux. Now, how we could do it, since the upper band has precisely the opposite phase with respect to the lowest band, if we are able to use a superlattice to put in resonance the upper band here with the lowest band here, and vice versa, what we get a toy model of flux attachment. And so this is something is quite intriguing for us. And since my time is essentially over, I thank you for your attention. This is the joint group between theory and autonomous and experiment at ICFO. And now this is a fruitful collaboration that is going also beyond physics. But now the nice thing is that we are happy that we can also improve it even more within Quasimodo.
Nice ending point. Thank you so much. Do we have any questions? Yes, Luca.
So regarding the two body-bound states, so these are two particles sitting in the same site or in neighboring sites?
So this you see here, we can have both situations in the sense that if one is looking to the inverse mean radius, you see that depending on which regime you are, when they are deeply bound, they occupy just a bit more than one side, and then when you relax a bit, this open up.
And why they should be analogous to a soliton?
Because, yeah, there is this idea that is, so if we go back to Grigoriev Seminara, this chiral soliton is a classical one, but actually there is the possibility of considering the quantum one. So considering the quantum one and detecting them, so the gap between the spectrum of all this quantum state becomes so degenerate that if you put too many particles, it's impossible to see. But somehow, there is actually, what one expects in this model is that there is really the full competition, not just of single particle condensate, two particle condensate, but to all arbitrary number of condensate. It's clear that this is not something very accessible on the lattice, because if you start trying to put together three particles and they mostly coincide, you have losses. But at least theoretically, there should be the competition of all possible soliton state. It's not easy to extract the many-body now states, yes, and also to resolve it experimentally, although in Paris with with a different type of soliton, they manage, but it's tough.
Any more questions? Okay, so it seems like you started from that there was a debate, are those anions true or not? So here, definitely we can say those anions are real. Yes.
Yeah, these anions, so because somehow they coming back to, so this was really a querelle that almost destroyed the career of this poor Benetton Ravello, that he changed field at the end, because he was really taking a naive dimensional reduction with really the goal of seeing, constructing 1D anion. And there were some glitches in interpretation of how doing the limit that were found by Jacques and collaborator, but essentially Kundu demonstrated that they were both right, so that one could really cure. The problem is that if you do a thing with the single particle Hamiltonian, you have to end up putting a strange object that's just the product of a delta function that are hard to deal, but essentially the model is right, and indeed these are 1D anion.
Okay, so let's thank the speaker once again. Thank you.